Hello, I'm Said Mohammed Keshani, a PhD candidate in electrical and computer engineering at Iowa State University. In this video, I'll walk you through our work on two-dimensional compound message authentication code for lossy channels, where we demonstrate over 20% throughput gains using what we call 2D compounding. Let's start with why do we need integrity check? Well, in any communication systems, whether it's GPS, cellular networks, or satellite links, data packets travel through channels that are often unreliable or subject to adversarial interference. Without a way to verify integrity, attackers or just noise can tamper with packets. This means a receiver may unknowingly process corrupt information. To prevent this, we attach a message authentication code to each packet. The MAC acts like a digital fingerprint. If the packet contents change en route, the MAC won't match, and the receiver will discard the packet. However, adding a MAC to every packet introduces overhead, extra bits that must be transmitted and processed. In a resource-constrained or lossy wireless environments, this overhead can drastically reduce throughput and add extra latency. Imagine a drone navigating by GPS. If an attacker spoofs the signal and there is no integrity check, the drone can be misdirected. Spoofed GPS incidents have already caused misrouted cargo ships and navigational failures. Integrity is critical, but bandwidth is precious. How do we preserve security without sacrificing too much throughput and latency? The most common practice for MAC, as well as we call the traditional MAC, appends a separate tag to every message. If you have M messages, you send M tags. Simple but inefficient. Though some implementation allow for truncation of the MAC for better performance. This diminishes its security strength. Therefore, the goal is how to improve the performance and not compromise security. To this end, researchers have proposed aggregate or compound MAC, where multiple messages are grouped and a single MAC is calculated over the concatenation. If you have, say, 6 messages, you transmit one tag for them instead of 6. This reduces overhead when the channel is perfect. But in lossy channels, compound MACs becomes problematic. If any packet in the group is lost or corrupted, the entire group fails verification. In other words, one bad packet invalidates all the other in that group. Under non-negligible packet error rates, this leads to many wasted retransmission or lost data. Therefore, for lossy channel, a better scheme capable of pinpointing the modified packet is required. This brings us to our solution, the two-dimensional MAC. Imagine arranging messages into M by N grid, M rows and N columns, so that we compute one tag for each row and one tag for each column. That gives us M plus N tags in total for M by N messages. If a single packet in row I, column J is lost, only the tags for that row and column are affected. All other messages in the grid still have a row and column tag capable of verifying them. In contrast, a one-dimensional compound MAC would discard every message in its block after a single loss. Let's look at a quick example, where in the grid of 4x4, M10 is modified, shown in purple. In 1D MAC, the message M2 and M6 will fail verification, whereas in 2D MAC, they will be verified by R1 and R2 tags, respectively. This is possible because 2D MAC can pinpoint the modified packet since tag R3 and T2 verification fail, whereas 1D MAC just pinpoints the column where a message could have been modified. This improvement in performance, however, comes at the cost of transmitting more tags compared to 1D MAC. We can improve upon 2D MAC by using superposition coding, which we call 2DSC. Instead of sending every row tag as a separate tag, we superimpose each row tag onto the messages for that row. At the receiver, the decoding process extracts both the message bits and embedded tag bits. Column tags still need to be transmitted separately, one per column, similar to 1DMAC. With 2DSC, row tag costs 0 extra bits, and column tags remain same as 1DMAC. So, if you have n by n grid, you effectively send only n separate tags. The superposition step is shown in the figure. The row tags, R1 in the figure, pass through a different channel encoder with lower code rates to be padded with extra parity to match the length of the concatenated row messages. Then we allocate a fraction alpha of the transit power to the row tag and 1 minus alpha to the row messages. Note if alpha is 0, this scheme will be similar to 1DMAC. Now let's discuss the theoretical analysis. To compare these schemes rigorously, we need to model packet error probability under different channel conditions. We base our analysis on the finite block length code approximated by Polyansky et al. For a binary symmetric channel, the packet error rate is shown in this slide. In this formula, L is the block length, P is the bit error rate before decoding, R is the code rate, C is the channel capacity, and Q is the Gaussian Q function. Calculating the packet error probability for each of these schemes allow us to compare the performance under different channel conditions. Now, let's define the comparing metrics. Our performance metric is authenticated throughput, the expected verified information bits divided by total transmitted bits. As shown in the formula, the straight line M is the total message code word bit transmitted, and straight line T is the total tag code word bits that has been transmitted. R is the channel coding rate, and probability of verifying received MI is the probability that the message I is decoded and verified successfully. The denominator M plus T accounts for how many bits was sent in total. Message plus tags. In lossy channel, probability verify MI depends on per packet error probability PE for the message and the PE of its associated tags. The picture below shows the authentication throughput versus EBN naught for all the 4 schemes. The best performing scheme is highlighted. As you can see, at lower SNR, traditional scheme has the highest performance. In mid SNR, the 2DMAC has higher authentication throughput, whereas very high SNR, first the 2DSC and eventually 1DMAC and 2DSC equally perform better. This suggests that 2DMAC can increase the authenticated throughput for lossy environments, though for lossless scenarios, 1DMAC delivers better performance. Also, one takeaway is that tag to message ratio, indicating number of tags transmitted for a fixed number of messages, is an important metric that needs to be taken into consideration. In low SNR, the tag to message ratio must be closer to 1, and in higher SNR, this can be reduced accordingly. Next, we demonstrate our scheme performance on real-world Wi-Fi testbed. Our testbed on a real Wi-Fi 802.11b/g network was configured as follows. The transmitter side, equipped with Ubuntu 24.04 LTS with Intel Core i7 11700K CPU, with a webcam that was capturing real-time video stream packetized into block of 18 messages each. There were 3 implementations: traditional MAC transmitting 1 tag per message, 1DMAC transmitting 1 tag per 3 messages, 2DMAC used a 6x3 grid, 18 messages, where 6 row tags and 3 column tags were used. On the receiver side, there was a MacBook Air M3 version receiving all the UDP packets. To simulate an adversary, we randomly modified the packets with packet modification rates ranging from 1% to 30%. At each packet error rate, we transmitted thousands of frames and measured the resulting authenticated throughput. Here are the main takeaway from our experiments. 2D Mac outperforms the other two in a small packet modification rate conditions. Traditional Mac performs best at packet modification rate more than 30%, improving the analytical results. Overall, the experiments line up very well with our theoretical modeling. Two-dimensional structure yields significant authenticated throughput gains in lossy wireless environments. Now, let's wrap up with the key takeaways. Traditional and 1D Mac attach one tag per message or multiple messages that is straightforward but very inefficient in lossy channels. Two-dimensional Mac arranges messages in an m by n grid and compute one tag per row and one tag per column. This uses only m plus n tags for m by n messages and localize the impact of packet loss at the cost of more tags compared to 1D Mac. 2D superposition coding embeds row tags within the message, so only column tags remain separated. This reduced tag overhead, balancing the trade-off between the number of tags and the authentication throughput gains. We showed over 20% higher authentication throughput compared to traditional Mac in moderate to high packet error rate regimes. Thank you for listening, and send me an email at kashani@istate.edu for any questions that you might have. Thank you.